Okay. Today I'm going to talk about the online coloring, and actually this work was started last year when Seogjin visited here, and then he introduced several problems at that time, and then so luckily we made some progress. Yeah. So first, okay, my talk consists of this way. I mean, first I'm going to explain what is online coloring, and then what is the interesting problem, and then result, and some sketch of proof. Okay, online coloring is a game. So we have two people. So typically we say Alice and Bob, and then so Alice presents some subset of vertex, and then Bob color among the vertex. And then actually Alice is able to select the VI at each I step, and then so there's one restriction, and such that each vertex can appear at most k times until it is colored. So in this case, who wins? So if Bob is able to color all vertex, then Bob wins. But if Bob cannot color all vertex, then Alice wins. So here the main object is Alice select a subset of vertex so that Bob cannot complete the color. But Bob want to color nicely so that he can complete the coloring. So
when V1 is colored,
yeah.
you keep the same color.
Yeah.
And then you go to V2, or the color is changed.
Could you say again?
Maybe give an example.
Yeah. Yes. So just before I realized I need to prepare an example, but I forgot. I mean, okay, let me try once. Okay, maybe this is better. Okay, this example will be used again. Okay, here we have a vertex V1, V2, and V3, V4. And then Y1, Y2, Y3. So Alice to select, okay. Alice present Y1 and Y2. And then maybe Bob color Y2. This one. The next. Okay, here so each vertex appear 2 times. So next, Alice present. Okay, if white is colored, so Y1 and V3. So in this case, Y1 already selected 2 times, right? So yeah. So in this case, Bob must color Y1. Otherwise, next time, Y1 can be colored. So next.
So why is it only colored in one vertex?
So V3 also, I mean,
okay, yeah.
choose V3 as well, right?
Yeah. So maybe if Alice present this way, So in this case, maybe Bob can color with several vertex with this one, this one, this one, because they are independent set. So in this case, Bob can color all these three vertex. But this way, the problem is not good for Alice. Okay, later let me try this case. Let me check this case.
So when you say color, if you have a set of colors that are assigned, or if
So the
is it like a proper coloring, or
Proper coloring. The coloring should be proper coloring.
If Bob select some subset of Vi, then those vertices will have color I.
Yeah.
So Bob wanna
so
select
like
the
each step one color.
Yeah.
So that's why in this step you just color one vertex because there is an edge between them.
Right.
Okay.
So Bob wanna select the independent subset of Vi.
Okay.
We continue doing this.
So next, if Bob select V3 as, okay, in this case, Y1 must be colored. The next, V3 and V1, V2. In this case, again, no, maybe not yet. In this case, one must select this one, right? Wait a minute. Let me check a minute. Okay, so. So if go, okay, this way is in this case V1, V2 only appear one time. So next case V1 and V4. So in this case V1 must select, right? Wait a minute. Now V2 and then V4. What happened?
So yeah.
So the remaining chance is this only one, right?
So we lost.
So V4 has to be chosen.
Yeah. If V4 is chosen, then V2 has no more chance.
Right. Okay. So both of them has to be chosen.
Yeah.
So we lose it.
Yeah. So the key point is, one of the key points is, here's the restriction, each vertex, how many choices? There's one key point is, so another point is, actually there's, so this, this information is actually key point. I mean, each vertex, for each vertex, how many chance it has. And then, so if this vertex has 3 choices, then we can complete this coloring. Bob is able to color this. So what happened here? If Alice select V1 as you said, V1, V3, Y2, V2. So in this case, V1, V2, V3, V4, Y1, Y2, Y3. So in this case, well, what is Bob's choice?
I will take them all. Oh, make it independent, right?
Yeah. And so he might take this way.
Okay.
Then the chance of this is remain 1, right? So next, V3 and Y2, V4. Then Bob colored this one, Y3, and the color this one. Well, either is okay, right? So next, if L is present, okay, Y1 and V4. So in this case, Bob color this one, and he can complete the coloring. So this way, this choice is not good for Alice. So always the game. I mean, Alice tried to make a bad case, and always Bob tried to complete the coloring. So I hope that now the meaning of online coloring is clear. Actually, this one is the generalized concept of the list coloring. So let's just do this one. So for instance, okay, if the list is this way, then actually it's the same as V1 means the vertex. Okay, let's V1, V2, V3, V4, Y1, Y2, Y3. Actually, V1 is the set of vertex which has the color 1 in the list. So V1, V2, V4, Y2,
Y3.
Y3. And then V2 is the vertex, set of vertex which has color 2. So only V1, V2, Y1, Y3. And third set is V3, Y1, Y2. The final presentation, final case is V3, V4. So if L is present this way, then okay. So if here the least chromatic number of this graph is 2, then it means if L is present this way, always Bob is able to finish the coloring. So this way, online coloring is the generalization of. Actually, online coloring is a generalization of the list coloring. Then what is the difference? The difference is in the list coloring, in the beginning, we set up V1, V2, V3, V4, and then fixed, no change. But online coloring, okay, if Alice select V1 and then Bob color some vertex, and then after this reaction, Alice present another subset. That's difference. So as I present, actually this one is the least chromatic number is 2, but okay, here what is the online chromatic number? Online choice number is actually the smallest k, and then there's a graph such that whose online choice number is bigger than least chromatic number. Actually, this is one example. So just before I showed you, if each vertex has 2 choices, but still, yeah, there's one strategy of Alice, so that Bob cannot complete the coloring. So it means online choice number of this one is bigger than 2. So far clear? Yeah. And then shouldn't you show that get some general upper bound of online choice number is he obtained this upper bound chromatic number times log n plus 1. And then some terminology that's we say chromatic choosable if the least chromatic number is same as chromatic number, and then online chromatic choosable if online choice number is equal to chromatic number. So actually we are interested in this type of graph. So there's famous conjecture by Ohba in 2002. So if the number of, actually there's some type of the number of vertex is at most 2 times chromatic number plus 1, then is the least chromatic number is same as the chromatic number. And then so one example, so actually this is a 2, 2, 2, 3. And then this chromatic number is 4. And then also the least chromatic number is 4. And then what is the number of vertex? It's actually the same as this one, right? So, and then, so from now on, so we use this type of the notation of a star. Here, what's the meaning is K1 star K1 N1 and then N2 star K2. What does it mean is K N1 N1 what does it mean? N1 and then N2 N2 N2. how many times? This is K1 times, and this is K2 times. So this is here. What is the meaning of K5 star 3? Is 5 appear 3 times, and then 4 appear 2 times. So for this one, so with the notation, we can say this one is, how can you say? 2 star 3 and 3. And then regarding Ohba's conjecture, there's some progress with the Ohba's conjecture. In the general upper bound, general bound result is this way. If the number of vertices is at most this one, then this conjecture is true. And then also Reed and Sudakov show that okay, this conjecture is true asymptotically. I mean, if the number of vertices sufficiently large, then the conjecture is true. But there's one slight difference. Here, at most two times chromatic number plus 1, but this one is actually less than 2. There's a slight gap, still gap. And then lesson 3, Kostachika and Stevich and Udall show that okay, this conjecture is true if each subset has at most 5 vertices. It means there's a complete multipartite such that so each subset has at most 5 vertices, then the Ohba's conjecture is true. And here we might have a question. Why the cancel only complete multipartite? Because the conjecture is for all graph, not only complete multipartite. The reason is this way. If chromatic number is k, what does it mean? There's a k independent set, and then there's edge between independent set. So in this way, actually the number of vertex and the chromatic number actually not the same, even though we add all edge. Right? So actually the complete multipartite is the extremal case. So it means if we show that the conjecture is true for complete multipartite, then
this is true for just general coloring.
yeah.
What about this coloring?
Yeah.
Isn't it going to be the same when you add those two?
We only increase the choice number.
Yeah. Yeah.
Okay.
Yeah. So even though we had more edge here, still the chromatic number is same, and the number of vertex is same. Yeah. And this, okay, from Ohba's conjecture, from this, so we have a online version of Ohba's conjecture. So these 3 people conjectured if the number of vertex is at most 2 times number chromatic number plus 1, then online choice number is equal to the chromatin number. And also they proved, okay, K, so this graph is online K choosable. It means so it means each subset has two vertices. In this case, the chromatin number, in this case, it means the chromatin number and online choice number is same as K. And then they tried to prove this. They believed this conjecture is true, but last year, when Schrödinger visited here, then one of our authors found this example. The conjecture is not true. And then we generalize, so we are able to show that, okay, for this graph, online choice number is bigger than chromatin number. And then this graph satisfied actually this condition. So we need a new conjecture. So new conjecture is number of vertices at most 2 times chromatin number. So in this conjecture, actually this theorem is tight, right? And then they show that to show this, they used combinatorial Nullstellensatz. Actually, the most proof regarding this problem is the techniques is using Holst theorem. So, but problem is the Holst theorem cannot be used in online coloring. The reason is Holst theorem. To use Holst theorem, we need to figure out each vertex, which neighbor it has in advance. But in online coloring, we don't have such information. So question is there another proof without using combinatorial Nullstellensatz or without using Holst theorem? I mean, in general case. And then our result is, okay, actually this result is already proved by using combinatorial Nullstellensatz. But we give another proof, that is, actually we use mathematical induction. Actually this is first proof of least chromatin number of this graph is K without using Holst theorem. And then another result is, okay, for this graph, we show that online choice number is exactly K plus 1. And then here another question. Okay, each set has 2 vertices. Okay, the yellow color means the number of chance for each vertex. So here, wait a minute. So it means each vertex has 4 choices, right? So in this condition, with this condition, so this result imply Bob cannot complete the coloring. Because here k is 4, right? So here the meaning is k plus 1 is this is greater than k. So we have one question. So what happens if one vertex has more choice? Then can Bob finish the coloring? What do you think? So what happens instead of 5 if we increase to 6? Actually, then in this case we have more freedom, right? And then can Bob finish the coloring? So the last result imply
But I don't understand the notation in the last.
oh yeah. That is, it means this implies the number of chance for each vertex. So this one is, what is that? K minus 1 set. And this one is the last set. Actually, that is just this one. But this appears k minus 1 times. So we just denote k minus 1 and then divide the case. So here what does it mean is, so if the last vertex has 2k minus 2 and then previous and the other vertex k choices, in this case, Bob is able to color, but if the last vertex has one small chance, number of chances is smaller than 2k minus 2, then Alice has a strategy so that Bob cannot finish the coloring. Do you have a question?
Just maybe not something, but when you say unlike k choosable,
Yeah.
we have the chances for vertices must be at most k.
Yeah.
So, but here you have like 2k minus
2, yeah.
So
So this is a little generalized case. I mean, each vertex may have a different.
oh, so that's the notation
Yeah,
for generalized
yeah,
k
yeah.
choosability.
Right.
Okay.
So the proof is looks ugly here. So the key point is, let me explain briefly the key point. Actually, we want to show that if each vertex has k choices, then Bob is able to coloring. But here's actually the strong version of mathematical induction. That is, we consider some set xk minus 1, next some vertex has only one vertex, some set. This is still complete bipartite. Then how many? This is k minus 1. And this is k2. So k minus 1 and k1 plus k2 is k. So we use induction with this model. And then, so here what's the meaning is, so once example is like this. What is this? Here K2 is 2, K1 is 2. Okay, this correspond two one vertex and two vertex. And then this is actually how much? K2 plus 1. This is K2 plus 2. So this is first requirement. And the second requirement, what is total here? Total is, second requirement is each vertex is at most k plus 2, k2. And the sum of these two is number of vertex. So here,
so this f will eventually be the function denoting the number of times it appears.
So actually. So this model is actually the generalized situation. And then we use induction with this model, and then we delete one vertex, delete one vertex nicely. Then still the new graph satisfies this condition.
And when you say feasible, it means
satisfy this condition. Feasible means the Bob is able to coloring. No. Here the feasible means how can you understand this?
Feasible means Bob must have a winning strategy.
Yes. So this is just we delete one vertex nicely. Then still the new graph satisfies this condition, and by induction, the new graph is feasible. The new graph is feasible. That means the Bob is able to coloring, and then also Bob can color this one at the last moment. Okay, so here is one strategy. That if Alice present a subset U, and then Bob select independent set I, and then we have a new graph G prime, and then still new graph satisfies the condition, and then we modify the number the function f and the g this way, and then so finally we complete the Bob can we can show that the Bob can complete the coloring. Okay. So let me give you one example. Okay, our model is one vertex of two set and two vertex of two set. And then, so here what happened if Alex present selected this way. This is U. Then we have two choices. Case one is maybe Alex select this one. So in this case, what is the new set that is 2, 3, 1, 4, 2, 3. Because this vertex selected already one time, so number of chance is decreased by 1. Also this one decreased by 1. But this vertex, no change. And then next, what happens if Alice select this one? And then new graph has this way. So 3, 1, 4, 2, 3. So here, so if Bob is able to color with this condition, then actually it means Bob can complete the coloring of the whole graph. So actually the basic idea is this way. So here's case 1, 2, 3. Case 1 and 2 means, so if it represents, if Alice has freedom. Alice can choose any subset, but still Bob has a strategy. If Alice presented this way and Bob selected this way, and Alice presented this way and Bob selected this way, and then finally through this way, the new graph also still satisfies this condition. So that's the key idea of the proof. And then to prove this, we have more complicated cases. The reason is you have some subset of one vertex, and some subset of two vertices, and the one subset has three vertices. So we have a little more complicated situation, but still you are able to show that the new graph satisfies this condition and use induction. So through that way, so we can complete this theorem. Okay, let me show that the one example of this, why this is not good. So here, when k is 5, it means 2k minus 3 is 7. It means 5, 5. So now, Alex presented this one. Then what is Bob's choice? We have only two cases. One is this one. Another case is this one. So case A, in this case, new graph yeah, it's okay. Maybe second case is more easy. If Bob selected this one, then new graph is and then what is Alice's choice? Alice select this. So now, can Bob color this one? If Bob color this one, then remaining graph. What does it mean? This one is 4 independent cells and each vertex has only 3 choices. And then this one is actually form K4, but only 3 choices. So we cannot finish coloring. So this case forces to Bob to select this one. And then Alice is bad person, so select also this. Then again, maybe Bob must select this way or this one. But actually either one is the same situation. I mean the similar pattern. And then next, this way, it means then so one more time, if Alice presents this one, and this is only one chance, so you must color this. So 2, 3, 4, 1, 1, 3. Then next, Alice to present this way. Then what is Bob's choice? Must select this one. So 1, 2, 3, 4, 3. So what is the problem here? Actually, this form K5, but each vertex has at most 4 choices. So we cannot complete the coloring.
Because K5 is not 4 choosable.
Right. So through this way, Alice has a strategy. Alice has a winning strategy. And then, but this case, we can show that using mathematical induction again, and then Bob has a winning strategy. So, okay. And then lastly, actually last year, someone can pronounce this person, I mean, he came from Poland.
Is Kuba a Czech person? Jacob Kuba?
I think this person is friend of him.
Yeah, but
I think, but this person came from Poland. So I think Poland.
But Kuba visited KAIST
KAIST?
and last year. But
Oh, really? So when I visit Zhejiang Normal University last year summer, so we call him Peter, Peter, because it's very hard. So we don't know how to pronounce it. I don't know. Shouldn't just say. He just say him. He call him as Peter. So these three people prove that online version of Ohba's conjecture is true if the independent size, the number of vertex of each subset is m minus 3. But there's one thing.
so this is when the number of vertices is at most twice correcting number plus 1.
I don't know, just
The modified one.
yeah, modified one. Just this. And then in this case, number of chance is just exactly kk. Wait a minute. I saw what you mean. This graph does not satisfy this condition.
Right. So
Yeah.
plus 1.
Too many. I see. Many is, yes. Many isolated bodies. Okay. Actually, this is my first time of presenting this paper, so I'm sorry, I was not well prepared this talk, and also it seems it's very hard to explain in English. So thank you for your attention.